Hi, welcome to Data Science for Ecologists in R. My name is Ruairi Josifek, and this is the first of 3 videos in which I'll introduce and discuss polynomial regression analysis. Specifically, I'll cover the framework and utility of the method, the corresponding statistical assumptions, the use of raw versus orthogonal transformations, variance partitioning, and some limitations of the analysis. This video will focus on the model framework, intending to answer the question, what is polynomial regression and why use it? So polynomial regression is derived from the multiple linear regression framework, which estimates a response or y variable value using corresponding values of 2 or more predictor or x variables, along with calculated intercept and slope coefficients, all the while allowing for random errors with a normal distribution centered around 0. So if you're still here, then you're probably familiar with this. However, if it's new to you, I encourage you to first go and watch our earlier videos on linear models, since this is the foundation on which the polynomial regression was developed. The linearity of coefficients in this model implies a linear relationship between the x and y variables. However, as we know, relationships are often much more complex than this in natural systems. So polynomial regression allows for modeling of nonlinear relationships within the framework of the multiple linear regression. Where in multiple linear regression, each slope coefficient, i.e. beta 1 to beta k here, is associated with a unique independent random variable, in polynomial regression, a new slope coefficient is calculated per polynomial term included in the model. While there's no defined limit to the number of polynomial orders that can be included, issues will arise with the inclusion of higher orders, which will be discussed in the upcoming videos. For now, let's look at an example using simulated data taken from R to illustrate how such a model can be fitted. So first we can simulate an independent x variable using the RUnif function, which takes a random sample, here of 100 data points, from a uniform distribution, here with a range from -3 to +3. Next we can simulate a dependent y variable using the rnorm function, which takes a random sample, here again of 100 data points, from a normal distribution, here with a mean value of 2.5x plus -2.5x squared and a standard deviation of 4. The mean value provided here ensures a quadratic relationship with the x variable, while the standard deviation introduces simulated random error, as shown in the plotted data. So we can now, for comparative purposes, regress y on x in a simple linear model using the base R lm function with the syntax y tilde x. We can then call a summary of the fitted model using the summary function as shown. So we can see from the resulting plot that the model fails to capture the overall trend in the data, despite the extremely significant result. This is further evidenced by the r² value, which in summary is telling us that only approximately 22% of the variation in the data is captured by this model. Let's now contrast this result with that of a polynomial regression model, fitted to the same data with inclusion of a quadratic x term. So there are a number of ways to include this term within the model formula in the lm function. However, for reasons that will become clear in the next video, we're going to make use of a nested poly function from the base R stats package, as is shown here. The syntax is straightforward, whereby the first argument calls the data to be transformed, and the second argument simply defines the highest order of polynomial transformation, since all lower orders will be included in the model. The final argument shown here relates to the transformation method, which we'll cover in more detail in the next video. For now, it's sufficient to say that the argument raw equals true ensures that each transformation is applied directly to the x variable, i.e. if untransformed x equals 5, then transformed x equals 25. A summary of the fitted model can now be called, again using the summary function. So it's clear from the plot that the polynomial model better captures the variation in the data, and this is first confirmed by the adjusted r² value in the model summary, which in essence tells us that the extent of data variation captured by the model has increased from approximately 22 to approximately 78%. However, let's not put our feet up just yet, since we still have to confirm that the assumptions of the model have been met, and this is where we'll pick up from in the next video. So until then.